How NASA Landed on the Moon. A Story of Physics and Ingenuity, Part 1. In the summer of 1969, humanity achieved something that had lived only in dreams and science fiction. 2 astronauts stepping onto the lunar surface. This was not magic, nor was it a lucky gamble. It was the result of decades of scientific understanding, engineering mastery, and human courage. To appreciate how NASA accomplished this feat, and to silence the myths that claim it never happened, we need to walk through the journey, guided by the laws of physics that made it possible. The story begins with a challenge. In 1961, President John F. Kennedy stood before Congress and declared that the United States would land a man on the moon and return him safely to Earth before the decade was out. It was a bold promise, driven by the urgency of the Cold War and the space race. But beyond politics, it was a call to push the boundaries of science and engineering, to do something no one had ever done before. At the heart of Apollo's success were principles discovered centuries earlier by Isaac Newton. His first law, the law of inertia, tells us that an object in motion will stay in motion unless acted upon by an external force. Imagine sliding a hockey puck across a sheet of ice. It glides effortlessly until friction slows it down. In space, there is no friction. So once Apollo left Earth's orbit, it could coast silently toward the moon for 3 days without firing its engines. That simple truth saved enormous amounts of fuel. Newton's second law, expressed as force equals mass times acceleration, explains why the Saturn V rocket, the most powerful ever built, had to shed weight as it climbed. Picture pushing a bicycle compared to pushing a car. The heavier the object, the more force you need. Apollo's engineers knew this, so they designed the rocket in stages. Each stage burned through its fuel and then fell away, leaving the remaining vehicle lighter and easier to accelerate. The third law, the principle of action and reaction, is the essence of rocket propulsion. For every action, there is an equal and opposite reaction. If you've ever let go of a balloon and watched it zip around the room as air escapes, you've seen this law in action. Rockets work the same way, expelling exhaust gases downward so the vehicle moves upward. Finally, the law of universal gravitation governed the entire voyage. Every object with mass attracts every other object, and the strength of that pull depends on their masses and the distance between them. Think of gravity as an invisible elastic band. The closer you are, the tighter the pull. Apollo's trajectory was calculated with this law in mind, balancing Earth's grip and the moon as gentle tug to guide the spacecraft across 384,000 kilometers of space.